As we embark on our unit on non-measurement geometry, you will notice that we are going to attend to these terms. And a lot of these terms are actual geometric figures. We are going to focus on the definitions of geometric figures. We're going to focus on how to name them, whether you use 2 points, do you use the end points, can you use any 2 points, do you use 3 points? And then also we will have a shorthand labeling method, a shorthand technique for how to refer to them. And the concept that you're really trying to capture in this unit is there are a new set of rules for how to talk about geometric figures, how to label them. It's sort of a new language that we are going to adapt to. And additionally, we'll soon be drawing three-dimensional figures, and there's a new language that we will use to represent three-dimensionality. And once you sort of understand the rules, you can really start to make some more accurate figures and drawings. So as we embark on non-measurement geometry, the main concept that I want you to capture is a geometric figure is simply a set of points. You might be looking here at this gray square. That actually is the interior of the geometric figure. So we are only focusing on the set of points that are all along these red segments. And the union of those red segments creates what we recognize as a square. We are not focused on the interior. That is something that you look at when you look at measurement geometry and you talk about area. Right now we are not measuring anything. We are merely looking at the set of points, so we will rely on set notation. So right now, if I place my pencil right here, I am actually not touching this square. Right here, I'm not touching the square. But right here, yes, I am touching that square because I am lying on that set of points that defines that square. So let's start with some definitions. A point. It is an exact location in space. You represent it with a capital letter. If you are going to talk about it, you are going to say that X is next to Y, or sorry, next to W. Notice I'm not going to say point X. I'm also not going to write point X. I just reference it with a capital letter. Another thing you should notice is that my points do not have size. They are precise, exact locations in space. They are infinitely small and accurate. And so yes, while W looks larger than X, that is just the representation of this exact location in space. The dot might look larger, but the location is still a location. In the same way that whether you live in a small house or a mansion, you still have one address. We are also going to look at the set of all possible locations, and that is going to be the term we refer to as space. So a point is an exact location in space. Space is just what we're swimming in, the set of all possible locations. Now our first geometric figure. It's going to be a set of points between two endpoints and including those endpoints. Let's zoom in right here. This is not a segment because that creates this meandering curving curve that connects K and T. When we talk about between, we imply, and this is important to make a note of, between means straight path. So this is not a segment. As you can see down here, let's look at this figure first. Here we have segment XY. I am going to name the segment using its endpoints. That name is segment XY. Over here, this is segment BC. The way I write that in my shorthand is I write the endpoints BC with a bar over them, or a small segment. I could also write that as segment CB. On the right side, this is segment XY, or segment YX. Now D is not on that segment. Yes, you could swing by and pick up D on your way to school if you were Y, but No, D is not on the segment. It is not between X and Y. Between implies straight path. M does indeed lie on segment CB, but when I'm trying to capture this full set of points, all of these points, I want to refer to them as segment CB. If I were only referring to segment CM, I would not be talking about this complete figure. I would be ignoring these points by only referencing segment CM. So we need to be very accurate in terms of capturing the full set of points. The next geometric figure we will look at is a ray. A ray is like a segment, except you take off one of its ends and you allow it to continue on. So you take off one side of its stopping point. So a ray is a set of points starting at one endpoint. M is the endpoint here, W is the endpoint here. And you continue infinitely in a straight path. So here, this is called, on the left, is called ray WT. I start with W. It's weird that the starting point is called the end point. But I start with W and I pass through T. So I will call this ray WT, and I write it like this. Notice I do not have a dot on my arrow for ray WT. And notice this is a very different set of points than ray TW. Ray TW goes from here all the way to here. That's a very different set of points. Yes, it has this in common, but we're not talking about that set of points. So we're being very specific, and we only want the set of points that starts at W, being my endpoint, and continues through to T. On the right side, this is ray MR. Unlike a segment where we could call things forward and backwards, so we could call things BC or CB, a ray has a very specific starting endpoint, and that always has to go first. Again, make sure you do not put this dot right there. No. Interesting. Here comes a half line. That is a ray without its endpoint. Why couldn't you just call a ray without its endpoint a ray just without its endpoint? Well, because it's just so important in math that we want another name. We're going to call it a half line, and you're going to encounter this in geometry, in inequalities, in algebra. And here's what's handy about it, and here's why it's important. Suppose I have 3-year-olds, 4-year-olds, and 5-year-olds. And no matter what, suppose there's some weird human development thing, whereas if you are under the age of 4, you just always have to eat small things like Legos and you choke on them and it stinks. And so it's no fun to play with Legos with anybody under the age of 4. As soon as you turn 4 years old, you're still putting them in your mouth. It's annoying, right? And so you don't want those 4-year-olds with you either. But as soon as you're 4 years old and a day, then you can play with Legos. But here's the thing. So do I make my ray start just after like 4 years old and a day? Is that where I would make it start? But then you might say, but like, wait, I'm 4 years old and like 12 hours. And so it's like, oh, okay, well, let's just zoom in and we'll just include that. So we'll make the start there. And it's like, wait, what if I'm 4 years old in like a minute? And so as you can see, we can always find a point infinitely between 2 points. And so it comes in handy to say, hey, look, you got to be older than 4. That's all I ask. And so our half line doesn't start at 4. It sort of does start, but it doesn't include it. And you create that with an open circle. If you are interested in inequalities, you would write this as x is greater than 4, whereas a ray would be x is greater than or equal to 4. So this half line down here is half line KT. Like a ray, it has to start at the endpoint that actually isn't included, and And unlike the ray, I do actually include the open circle to imply that it is a half line. And by the way, my Lego example is pretty lame. Moving on though. An angle. It's a set of points. It's the union of two rays. This angle is the union of two rays. Think about what two rays it is. Have that in your head. Okay, so it's the union of ray RK and also the union of ray RW. Now, you could also call ray RW RT. It's the same set of points. So if I unite those, because remember we're talking about sets, and in set theory we talked about intersection and union. So if I take the union of two rays with a common endpoint, I'll get an angle. R is very important in this situation. It is the vertex. And you'll notice when I name this angle, I'm going to use 3 points. 1 point from one ray, the vertex, and another point from another ray. So I could call this angle TRK. I could also call it angle WRK. So notice again, I have a point from one of the rays, a point from the other ray, and then in the middle is the vertex. Now, there are two other ways I could also reference this angle. I could also call it angle KRT or KRW. So those are all acceptable. Notice before we had ray RK, right? We had segment RK. We had half line RK. All of those went on top of the points. Notice the angle goes in front. Again, notice do not do little arrowheads on your angle. That is not cool, not okay. Does it really make a difference? Like, would the world crash and crumble? No. But what this unit is about is learning those little details and those little rules that mathematicians expect you to learn so that in the future you can learn even more complex rules and be part of a more elite club where you can solve cooler things. So let me ask you this. Do you think you can measure an angle itself? Can I measure this angle? So think about, how would you write this angle? How would you write the name of this angle? You'd have the angle symbol in the front, and then you'd have PAX, or you could have XAP. Notice your vertex needs to go in the center. All right, can you measure this angle? Is my point right here on the angle? No, I'm on the interior. Is my point here on the angle? No. Is my point here on the angle? Yes. So remember, geometric figures are not the interior. They are simply the set of points. Now, is a ray finite or infinite? Can I measure a ray? No, because it's infinite. So can you measure an angle? No, because it is made up of two infinite pieces. Can you measure the interior? Yes. We all know there's a protractor, and this might be like, 49 degrees. That's not measuring the angle itself. That's not measuring the set of points. That is simply measuring the breadth, or the opening, or the space, or the interior. And that is different. Our next term, line. It's the union of two, what kind of rays? Two opposing rays. So here we have a line that has T, A, and Q on it. X is near it, sure, but X is not on that line. You might want to reference that T, A, and Q are what is called collinear, which means one line can contain them all. How many lines can contain X? If you were thinking infinite, you're right. An infinite number of lines can pass through X. How many lines can pass through both X and Q? Only one. One and only one line can contain X and Q. And as such, it takes 2 points to define or determine a line. So given that, when we label this line of my original drawing, My line TAQ, I could call that line TQ. I could call it line TA. I could call it line QA. I could call it line AT, line QT, and line AQ. Notice one thing's for sure, only 2 points are needed to determine a line, so I am not going to write this as line TAQ. Do not do a line TAQ. Ugh. All right, so I'm going to ask you to draw different figures, and so I might ask you to draw 3 different lines, line PQ, line PS, and line AS, and you might be so psyched and you'd be like, yeah, check it out, 3 different lines, line PQ, cool, line PS, yeah, line AS, and this would be so incredibly wrong. Why? You just told me that point P is right here. Oh, and a point is an exact location of space. And P is also right here. And I'm thinking, wait, that's 2 different locations. How is that possible? And you're like, yeah, and S is here and also here, but they're exact locations. Okay, no, you can't do that. In a single figure, you cannot repeat points. So, how might you draw 3 separate lines? Well, you could have line PQ. Let's have line PS. And here's line AS. Cool. All 3 separate lines. Sweet. Notice I could not have put those all on one line because I asked for 3 different lines. Here come some pet peeves and common errors. Is this right here angle PQR? Kind of looks like it, I agree. No, it's not. I just see segment PQ and I see segment QR. An angle is made up of 2 rays, the union of 2 rays with a common endpoint. So I would need to have some rays actually extend and some arrowheads on this figure to make that actually angle PQR. Is this angle ACB? Well, I see AC and B. Cool. But wait, upon closer examination, this needs to be the vertex. So angle ACB would actually be this red angle. Okay. So when you're drawing an angle, make sure you check that the vertex is the point in the center. All right. Now, this is just a pet peeve. It's really not mathematically incorrect, but I cannot stand when people don't leave enough space between the dot indicating the point and their arrowhead. We're in infinite space here, people. There's no distance. We're not measuring anything. Can you please give T maybe a location a little further away from the arrowhead, or continue the arrowhead a little further away? Can't stand when I'm like, wait, is there a point there? And I'm like, where's T? T's just floating out. And you're like, oh yeah, I put the dot like right in the arrowhead. And I'm like, dude, we're in infinite space, man. Take up some more space. Separate some stuff. All right. Is this the proper label for this figure? So I see this angle. Is this a proper label? Let's see, MOP or POM. My vertex is O. Great. No, it's not the proper label. Ding, ding. Get these arrowheads out of there. We do not want those arrowheads. All right, let's check this out. Is this ray WM? Is this how I would write ray WM? It's not the drawing, but just is this how I would label ray WM? No, because I have that stupid dot there. The correct way to label ray WM is with no dot. No dot. All right, now, is this actually a legit drawing of ray WM? No. Why? Because ray WM starts at W. This ray starts at M. This is actually ray MW. And by the way, you would never write this as ray MW. That is, ugh, no. Your arrowhead always goes to the right. And so finally, a plane. Let's talk about a plane. We've done lines and angles. Okay, a plane is a geometric figure is always a set of points. Continuing infinitely along a flat surface in all directions. Your desk is part of a plane. The floor extends out into the hallway. It goes through the wall, really. Now, at some point it stops, but theoretically, that plane that your floor is on, or that your floor represents, could theoretically extend infinitely. The way you name a plane. Like an angle, you put the symbol in front of the letters you will use. You can use a cursive lowercase letter with a parallelogram, or you can use 3 non-collinear points. I could also call this plane y, w, x. The order does not matter. I'm not going to go through writing all the possible variations of x, y, and w. Just know that I need 3 non-collinear points to define a plane. Over here, do you think I can call this plane ABC? No, because these guys are collinear. So the only thing I could call this plane is plane Y. I have to use the cursive letter because these are collinear points. So if you think about a plane, you need 3 non-collinear points. So think about a stool, right? Some stool that you're sitting on. Fortunately, that picture sort of worked. Not really. Have you ever been sitting at a table or a stool and you sort of lean one way and like it settles, but then you lean the other way and one leg goes down? Yeah, it's hard to describe over a video, but those are basically different planes. And hopefully we'll talk about that in person. But just remember, a plane has 3 non-collinear points. All right. So you need blank points to define a plane. The correct answer is 3 non-collinear points. All right, so here we are. Let's practice labeling using our proper shorthand. All right, and remember, geometric figures, these figures are sets of points, so we're not measuring them. And so looking at this top left one, I see a plane, so I'm going to reference that with a parallelogram in front. I can't use the points given because I only have 2, so I can only call this plane Y. Top middle, I have a segment. That will be segment RT. The only other name I could give it is segment TR. Here's my ray. I know I don't use a dot, and I always go to the right. Even though this ray is going to the left, I always have to make my symbol or my label going to the right. Now I could call this ray MS. I could also call it ray MY. And that's it. I can't call it anything else because I have to start with M. Here I have a line, and I have a lot of options. Line CB, line BC, line QB, line BQ, line QC, line CQ. Okay, just make sure you're only using 2 points. What kind of figure is this? This is a half line. So this means I want all the points up close to N, but not actually including N. And you're like, well, why don't you just call it this point X and then just call it ray XL? Well, because as soon as I zoom in, I can see that there's a point between X and N. And so that's not working. And so this is a half line, and I will refer to that as half line NL. Here we have an angle. Remember, you do not put your arrowheads, and it goes out in front of your letters. Ouzo, that's a fun one. I could also write it Ozu. Down here, I don't have a cursive letter on this plane, but I do have 3, well, I have 4 points actually. So I could call this plane DEG, plane GED, plane GDE. Could I call it, though, plane EGF or GEF? No. Why not? They're collinear. Could I call it plane DGF? Yeah, sure, because those are 3 non-collinear points. This is just point H, just a capital letter. And here, what do I see? I see segment JI. I could also call that segment IJ. Yes, K is lying on it, but if I'm asking you to capture the full set of points, just tell me it's a segment IJ. That means I know it's definitely all of these. It means K is included.